Hi, and welcome to this quick tool review. This time around I have some tools that are both new to me and some that are completely new from the store and new to me. I want to start off with this silver and Deming bit. I've got it in a case that is from a different tool entirely, but I stored it in there just to protect it. And it's this 5/8 inch silver and Deming bit. And you can see here that it's 5/8 listed as high-speed steel right there, laser printed. And you can also see that it's really bent. So I was using this guy in my hand drill, my electric cordless drill, and I was cutting through some 1/4 inch stainless steel plate. And just as it was about to break through, it hung up, and you can see the flutes here caught, and they just got shredded. You can see the chunks out of them. Hopefully I didn't get too close there. And it bent the shank. And I was thinking, wow, with high-speed steel, I really didn't expect that behavior. I expected it to break, not bend first. So this totally surprised me. So I took this to my Rockwell hardness tester, and well, let's take a closer look. All right, so sometimes if you want to check the check hardness on something that's round, if the diameter is large enough, you can get away with it. But in this case, let's put in the appropriate holder so that we can make sure this is a better measurement. So let's start with the end of the drill bit here. And I'm just going to pick some part on the flute here. And we're just going to go around till this little dot gets lined up here. That means you're putting the proper preload, and let's hit 0. Okay, and release the pressure. I think I've got to adjust my air pot. There was a little bit too much bounce there. And look what we have. We have a Rockwell hardness of 59 at the tip there. So that's what I expect, right? High-speed steel, very, very hard, brittle. So let's go down here where the flute's got all gummed up. Go to preload, go to 0. Give it 20 seconds or so. If the hand's moving a lot, then you want to wait till it's settled, but there is an actual specific amount of time the force should be applied. I need to go look that up again. And now we are down to 56. And how about here? You notice how it's moving much more rapidly? That kind of says that this is much softer material. That means the indenter is actually pushing into the material. And we have a hardness so soft that it doesn't even show up on the Rockwell C scale again. I would have to switch to a B scale indenter, which is why this guy bent. And actually, when I went to an area closer to where these flutes really got destroyed, my first time before I did this, when I did this off camera, it came up with significantly softer. I think it was around 20. So they hardened just the tip of this drill bit, which is really weird. This is a made in China drill bit, fairly inexpensive. Silver and Deming, by the way, just as a little side note, Silver and Deming was a company. Two guys named something Silver and something Deming, and they sold these large drill bits with a reduced shank, and now all drill bits of this style are called Silver and Deming bits. In honor of the guys that originally. So you see right where the flutes got totally shredded here, you can see how soft it is because the hand's still moving really rapidly. And let's go back and see, that's too soft to even measure too. So it's not even measured consistently because on one part of the flute here, like up here, it measured a proper hardness, but just on the other side opposite it, it was much softer. You can see the big indent hole there. So I guess when you order these from China, be really careful. I guess that's just a common warning, but I thought it was really bizarre because this is probably high-speed steel because the end really is that hard. I measured in multiple places, and it really is right around Rockwell high 50s, the whole area, and it held up fine. The flutes, I guess, don't need to be quite as hard, but you would expect them to be hardened and just maybe chosen for a little bit more toughness. But I did not expect to bend a shank. I don't think I've ever bent a drill shank before, and I know it can happen, but I thought that was pretty odd, so I thought I would share. Alrighty, so next up is the mini Standridge surface plate that I bought from Tom Lipton. Tom Lipton had Standridge make a bunch of these for him a bunch of years ago, and they're not just a little gimmick. They are actually a ground grade A surface plate. See, they even graded it back 5/24/2019, which I guess is sometime close around when Tom bought these. This is an actual really flat surface, and I thought I'd put it to good use. And so I saw this on another guy's channel and thought, wow, what a brilliant idea. So what you use this for is an indicator holder on a magnetic chuck. You could also use this on the surface plate itself. There's no reason you can't. But in a magnetic chuck situation, all of your normal surface gauges are made out of steel, and they'll stick, so you can't move them around. This will actually let you slide across that chuck. You got to make sure it's very clean, of course. You don't want to go scratching this with like grit from the wheel. But anyways, I took a stainless steel puck, drilled and tapped it for 1/4 Now, Noga does make arms in 1/4 I believe. I don't. This one is not. This one's actually metric, just like this import one is here. So I drilled a 1/4 so I could order the right Noga, but I made an adapter here. So this just is a piece of stainless steel, 1/4 on one side with a screw Loctited in, cut off the end, 5 millimeter, 0.8 millimeters per thread on that side, and we can mount our indicator on here. Give it a little tighten, which will tighten both incidentally. And now we've got an indicator holder for the surface plate, which is really handy because I've needed it on multiple occasions. Maybe it was Mr. Renzetti, Robin Renzetti, I'm not sure. But being able to indicate things on the surface, on the magnetic chuck are really important. Quite often, like you're trying to orient a part on a vise and keep it straight, make sure that it's level across, you need to run the indicator, you need to slide the indicator across it. So without something that you can trust being flat on the bottom and non-magnetic, you're gonna have a bit of a challenge. And the advantage is that granite is harder than most steels, I think all steels. And so sliding it along the magnetic chuck won't wear it out. Now, of course, there's grit from the wheel. That's going to be a problem, so you got to be very careful. But this is a really handy tool to have that I now can add to my arsenal. And I mean to do this for a while, I just hadn't gotten around to it, so I thought I'd share. By the way, the pliers I used here, these are, I purchased on Amazon. These are soft touch pliers. You can buy new replacement jaws for them. I think they're nylon jaws. I use them a lot because they're non-marring. So handy. I've got actually 2 pairs of these in different sizes. Sorry, I just bumped you there. I got a bigger size and a smaller size. Very handy to have. Definitely recommend. Like again, replaceable jaws. They're not terribly expensive either. All right, so next up is a tool that I bought because, well, it's just plain beautiful. And it might be useful. I currently had a precision straight edge that is from the Soviet Union, Russia, triple CP. And it's a beautiful piece of work, and you can use it for finding how square an edge is by putting it up against something like the cylinder square and seeing whether any light comes through. But this is a really long one, so if you're working on something small, this might be too big. So as a solution, I bought this guy here, and it's really beautiful. Look at this guy. So this guy's really handy because it has 2 ground flat square sides that are parallel to the opposite knife edge sides. And so if this were on a surface plate, you could walk this right up to the device you're interested in checking, or the part you're interested in checking its surface flatness, and you'd be good to go, because you can put a light behind it and check and see if you see anything coming through. And if you don't, then it's flat and square. And if you just have a tiny gap, like if I lean this so that it doesn't make perfect contact anymore, then what you'll start to see is blue and then full light through. And I think blue is a couple tenths out of square. So this is a really handy tool, and it's a lot handier than the traditional just one piece knife edge without any square sides. I mean, this one has its place too if you're trying to do some long part. This is great for using on a surface plate, on your milling surface, if you need to have something, make sure it's perfectly square to the table as well. It's a very handy tool to have. Next up is a tool I needed for an upcoming video, and it's a simple Nico digital tachometer. I've heard the brand before. I don't know if it's any good. It was only 20 something bucks on Amazon. They claim it's good from 2.5 to 99,999 RPM, measuring from 2 to 20 inches away, accuracy 0.05%, which is pretty darn good. That's 5 in 10,000. So that would be off by potentially 50 RPM out of 100,000. So that's pretty darn small. They all seem to be about the same accuracy. So spending a lot more, like 6 and 8 times more, doesn't buy you more accuracy, at least according to specs. But in reality, they may be more accurate. I don't know the answer to that. And this is a laser tachometer. So there are some that have a physical wheel that stick out the end. I have an old-fashioned version of tachometer like that. Let's see, where did I put it? Let me grab that. Here we are. So this guy, you rub against a spinning wheel, and it ends up giving you the speed in RPMs. They make digital versions of these that on one side have a mechanical and the other side have an optical. I chose just to have optical. And all you need is something with a non-reflective surface followed by a reflective surface, and you can measure the RPM. They give you some reflective tape here that would be even better, and I could have used that. This is just a piece of aluminum. If you watched one of my last videos, this was a gauge I used to find the center of a part I screwed up. I'm just going to pop this guy into my drill chuck here. We'll start on the slowest speed. I haven't tested this yet, so let's see if it works. So here's my measuring. See if I can get this so you can see at the same time. Kind of challenging, isn't it? About 450 RPM, going to a faster speed on the drill motor. $1,400 RPM. This might be a little bit small because you'll notice the beam width here is kind of large, so that's not ideal. Ideally, you want just a tiny little point, a pinpoint. This is actually somewhat large. So you've got to probably have a bigger measuring surface. This is probably a little bit small. Let's see if I can find something a little bit larger to try. Since the smaller diameter was giving inconsistent readings, I'm going to try for a larger diameter, only because that spot size is so large. And I'm just going to use a silver Sharpie rather than the tape they provided, just as a test to see if it'll work. This center was only approximately found. It's not super precise. It might benefit from even just a piece of white masking tape. That might also work really well. We'll start with this, see how it works. Again, no precision intended here. Alrighty, so let's try measuring this, and we're going to shoot for the center of that. That is not giving me a consistent reading. And that might be the difference between a less expensive one and a more expensive one, so maybe lesson learned here. All right, we'll follow their recommended procedure So we're going to use a bit of their reflective tape. Let's see if it gives a consistent reading now, because the drill motor sounds like it's being fairly consistent. So let's go in the middle. All right, 900 RPM plus or minus a couple. That's good. Fairly consistent. Farther away, still fairly consistent. The farther away you get, the spot size tends to get a little bit bigger. For high speed. Not perfectly centered, so out of round a bit, but again, consistent measurement. Anyways, I think this is okay for being a $22 tachometer. I suspect the more expensive ones, even though they supposedly have the same accuracy, the spot size will be smaller and their measurement will be more consistent. So anyways, interesting tool. We'll be using it in an upcoming video to evaluate some stuff. Next up, these are not the new tool. These are a traditional crescent wrench, somewhat proportional. Jaws open up, you know, a little more for each larger size. I think the thinking behind that is that the jaw opening should be proportional to the length, meaning the wider it goes, the longer length you should need, because if you have a really big nut, you probably need a bigger lever arm to undo it. But what I find is that when you've got a small crescent wrench, a lot of times the capacity, if it was a little bit bigger, it'd be fine. What you're trying to undo is not so tight, it's just big. And so what I was looking for was a crescent wrench with a larger opening. And so the solution here is this guy. It's a Craftsman, and you notice it's really disproportionately large. And the jaw opens up hugely. It opens up more than the large crescent wrench does. So this is really handy if you're trying to put one tool in your pocket. Now, one thing that's really odd about this guy is that it keeps going and the jaw comes out. And you can put the jaw in backwards, and you're wondering, well, why would I want to do that? And the reason for that is it works on pipes as well. I'm not sure I'd ever want to do this, but it actually gives a really good bite on a regular round piece of material. You can see the jaw is biting in there. So they're hardened and chromed and designed to lock in as you tighten. So you just push in and rotate and it's in there. So you've got a crescent wrench that could also work on pipes. Now, I wasn't looking for that feature, nor had I ever seen one with a removable jaw. What I wanted was the ability to do really large bolts with a single crescent wrench. I thought that was really cool. So this is a Craftsman 8-inch, which I think is about the equivalent of this 200 millimeter. And you can see jaw capacity is significantly more on the Craftsman. And that's why I got it. But with an added bonus, it also works on pipes when you reverse the jaw, which is really odd and interesting all at the same time. Next up and last up is a tool that every machine shop should have that you may not be aware you need, or you're aware you need but didn't know there was a good solution for. No, it's not parallels. No, it's not the drawbar wrench for your mill that I made a long time ago with a chunk of brass brazed on the end. The problem is that parts tend to get magnetized. And when metal parts get magnetized, like these parallels or this drawbar wrench with all of the debris on the end, it's a total pain in the butt, because in the case of the drawbar wrench, you could drop all these little metal bits down into the spindle bearings. And for the parallels, if there's little bits of material on the ends of the parallel, they're not parallel anymore. They're not a square flat surface. Everything has to be clean. So what's the solution? The solution is a demagnetizer, also known as a degausser. This one is a Kanetsu under the SPI moniker. And this one is a used one that I got on eBay, made in Japan. And all they are is a ton of coils of wire wrapped around a an iron core, and you run AC through it. That's it, very simple. And what happens is, because AC is alternating, that means that the north and south is rotating back and forth 60 times a second. And In order for something to be magnetized, like these parallels that stick together, here, let me even rotate them 90, that even stick together. What happens is the magnetic domains all get their north-souths, or a lot of them get their north-souths oriented together. And once they do that, they become magnetic. When they're random directions, they're non-magnetic. So the solution is to use a degausser, and they're pretty easy to use. So right now you can see these two parallels are magnetized. It even holds at 90 degrees. And all you do is you pop the guy on. and then slowly pull it out of the magnetic field, which is kind of hard when it's that strong. You could put it on just one of these sides, but it's better where the field is strongest, which is right here in the gap. And slowly remove it from the field. That will leave them, the domains, in a random orientation and completely non-magnetic. Another set of parallels. Magnetic field decreases with the square, completely non-magnetic. See all the little metal bits on there? Half the metal bits are left here. Now when I rub them off, they stay off. And that's it. Now, I ran this for, I don't know, what was that? That was like a minute and a half. This one is designed for 100% duty cycle under factor here. See 100%? Most of the ones out there are not 100%. They're like 50% or 25%. 50% means you can run it for 1 minute and has to cool for a minute. 25% means you can run it for 1 minute, needs to cool for 3 minutes. So 1 minute out of every 4. So it's very important that when you get one of these, you remember that. Also remember that you need to, just setting it on here is not good enough. You start with it closest to the strongest part of the magnetic field, which is in this gap here, and then you slowly bring it away to the best of your ability. And as it goes, the field's changing back and forth, and initially it's probably taking all the domains, or almost all the domains, and making them go back and forth. If you pull it away really quickly, they could all end up in one direction, and it would still be somewhat magnetized. If you, as a matter of fact, I could show that here. So let's see, if I pop this guy on here, and I just pull it off real quick, it has a little bit of a magnetic pull still. So in order to do that, to get rid of that, you put it where it's strongest, and then slowly remove the magnetic field. And as you get farther away, with the magnetic field decreasing with the square of the distance, fewer and fewer domains are affected by the field until eventually none of them are, and you end up with more randomized magnetic domains, and you end up with parallels that have been degaussed or demagnetized. A very handy tool to have. I used a degaussing coil for a lot of years. I had this one, but it's not very strong as far as removing magnetic field from things like parallels. It would probably work, but it might take a while because it's a fairly large loop, so the magnetic field's kind of strong. This is actually for degaussing cathode ray tubes. They tend to get magnetized. They have a screen inside that the electrons need to go through small holes in the screen. But as the electrons hit it over time with the intense electric field, it tends to magnetize that screen inside the tube. And so color picture tubes that need the electrons to go to the right color, your purity or the color evenness across the tube tends to get affected. So the degausser is to go across the back of the tube and degauss that screen inside. And I used it a lot at work in the early days when we had CRTs. Now there aren't any CRTs for the most part, so you don't need it. But in the metal shop, still runs across needing it all the time. I get parts as you cut them, end up getting magnetized, and you need to fix that because all the chips are sticking to it. And if you're trying to do precision work, everything needs to be clean, and if the chips won't come off, you can't make it clean. Anyways, thanks for watching. I hope you find it useful. Hope to see you next time.